All right, here we're learning in section 4.5. So our big learning targets today are we're going to be using residuals. We're really going to be just looking at what residuals are, and then we're going to use those to help us determine how well our line of best fit models our data. We're going to be using some technology today, and I'm going to show you a great online calculator, graphing calculator that you can always use if you don't have your own calculator. And then we're going to be looking at correlation and causation. So the first thing is just what is a residual? So a residual just tells me how different my point is from the line of best fit. So when we're looking at real life data, it generally does not fall in an exact line. So we have to make that scatter plot. Then we come up with a line of best fit, and that's just our equation that best models our data. So our residuals just kind of tell us how close we are to our data. And really that's all you kind of need to know about residuals. So let's look at this. So in example 3 in section 4.4, we're given this equation, y equals negative 2x plus 20 to model this data in this table. So then we're asked, is the model a good fit? So what we can do is we can take each of our x values and plug it into the equation and come up with a y value. And that's really what we're doing, is calculating those residuals by doing that. So I take my x value of 1, I plug it into my equation, and I end up with a y value of 19 from here. And if I plug it into my equation, I ended up with 18. So that difference would be 1. Well, let's use my next x value of 2. From my data, I was given a 15, but if I plug 2 into my equation, I end up with 16. So that difference is a negative 1. My next point 3, I was given a data point of 13, which is right here. Woo! But if I plug it in, I get a 14, so that difference is a negative 1. And I can just keep doing that as well. So then I plot those points on a graph, and I plot these points, the residual points. So this first one was a positive 1, this next one was a negative 1, then a negative 1. And we can see that they're kind of scattered around. There's a couple right on the x-axis, which means they were exactly the same. There's a couple above and a couple below. And so since they are spread out fairly evenly, is what this tells me, it says that yes, that line is a good fit. So let's look at another example. So here I'm given some data about ages and salaries in thousands of dollars of 8 employees at a company. I'm also given an equation to model this data, and I'm asked, is the model a good fit? Well, so again, I take all of these x values, which are my top ones, and I plug them into my equation and to help me get like the data that would come from that equation. So I go ahead and I plug them all in. Here's the y value I'm given from my data for each of my points, and here's the y value I got from the equation. So then I can calculate my residuals, just the difference between these two, and I get these values here. So then I plot these on my point, and you'll see that these are way scattered, and they look in kind of a shape. They look kind of like a U-shaped. So because they take a shape like that, and they're very scattered everywhere, it does not model my data well. And all we're really doing is seeing if these numbers are really close all the time, then yeah, it would model it really well. But here we can see this right here is a difference of 5. That's pretty far off. Also, this is a difference of 3.6. These are pretty big differences. So that would also tell me, without having to graph it, that my data doesn't fit very well. So here's one. If you want to try this one and see what you can, see what you come up with, go for it. Okay, so the next thing we're really going to look for is how can we find a line of best fit? And we know that this is what we're going to be doing whenever you see that word regression. Okay, using linear regression, we're going to eventually be using quadratic regression, but this just tells you what kind of equation, and this just tells you, okay, we're using some sort of technology to find the line of best fit. Okay, that technology will also give us a correlation coefficient, which tells us how close our model actually fits the data. Okay, so the closer to 1 is the better model it is. If it's negative 1, it's a strong negative correlation. And if we're close to 0, that means, yeah, there's no correlation. Our data just doesn't fit this model. Okay, so here we go. The table shows the duration in minutes, which is our x, right? So here's our minutes of several eruptions of the geyser at Old Faithful, and the times in minutes until the next eruption. So this is also in minutes. And I'm just like to label so I know exactly what I'm looking at. Okay. Using a graphing calculator, find the equation of a line of best fit, then plot the data and graph the equation in the same viewing window. So let's do that first. So instead of using a graphing calculator, I'm going to use Desmos. Okay. Because we always have access to Desmos, and this is just our website, desmos.com/calculator. So when I'm doing this linear regression, the first thing I want to do is I want to make a table. So in order to do that, let me move this over just a little bit. Never mind. So up here in Desmos, you'll see that you can add something. So you'll click on this and you'll add a table. And that's what I did here. So I add in all of my data, my X values and my Y values. Then in my next line, I go ahead and I type the equation of a line. So I know it's Y equals mx plus b. So now Desmos is saying, okay, great, we like mx plus b. Just tell me what you want. So we want to be very specific. So right after our Y and our X, I'm going to put the number 1. And I put the number 1 because that's the data that's up here. This is x1, y1. Well, now it's really mad because my data is not going to exactly fit. So I have to get rid of my equal sign and use this little squiggle, which is right above your tab key on the calculator. So now I can look and say, oh, now here's my slope is almost 12 and my y-intercept for my equation is 35.1. So now I can rewrite my equation. Okay. So now let's go back here. So that would be my equation. Okay. We don't really need to look at the graph. If you want to, you can zoom out to find it in Desmos. So let's look way up here, right? Because our data is up here further. So there's my line, and my data is going to all fit in kind of right here. It's really hard to see because of our labels. Okay. So now I'm being asked to identify and interpret the correlation coefficient. So here we go. Let's go back to Desmos and see what our correlation coefficient was. So you'll notice our correlation coefficient is always going to be R. So R, this R value, 0.9787, that is pretty close to 1. So that's going to tell me that it is a pretty strong positive, right? Because it's a positive R value. It's a positive correlation. And I really don't have to do anything with it other than that. Just say it's pretty close to 1 and it's positive, so it's a very strong positive correlation. So then the last part of our question was to interpret the slope and y-intercept of the line of best fit. So remember that our y value was time until the next eruption, and our x value was the duration of the next eruption. So we can find here the slope, which we said was almost 11, or almost 12, and the y-intercept, which was 35.1. So we can use that to help us with our next couple of graphs as well. Okay, so we used that Desmos to help us find that equation of the line of best fit. And we're going to then use that equation to help us with some other things in this example. So we're going to be using the equation of the line of best fit to approximate some things. So we were given the equation of y equals, we're going to just kind of round for this example, 12x plus 35. So when I have that equation, now I can use it with some of this data. So approximate the duration before a time of 77 minutes. So what do? I take this 77 minutes and I plug it into where I have my y value, right? Because it's talking about duration. So we're going to plug this in. So we're going to end up with 77 equals 12x plus 35. So when I have this, now I can just simply solve for that x value. Right? And I can do that by subtracting my 35 from both sides, which would give me 42 equals 12x. And then I can divide by 12 and divide by 12 and solve for my x value. Okay, so I've used the line of best fit that I got from Desmos and use that to help me extrapolate some more data. So now I'm being asked to predict the time after an eruption lasting 5 minutes. So this is where I can either substitute this in, but I also want to show you how you can use Desmos to do this as well. So if you look in the book, it shows you that you can use the trace feature in your calculator to find where our x value is about 5. But let me show you a way that you can do that using Desmos. So if I want to use Desmos, I can then click on a third line, and I know I'm dealing with my x values. So I'm going to say x equals 5. So you'll see that those are now both plotted on the same graph. So I can zoom in and move in to where I see they intersect. So using Desmos, I can do that, and I just click on them both, and it tells me, it gives me that point of where they intersect. So I would say that at 5 minutes, my y value would be a 95.057, and because that's where those two lines intersect. So I can either solve it algebraically, or I can solve it using Desmos. So let me show you this other cool thing that we can use Desmos for too. Since I know that this 77 minutes was my y value, I could have also used Desmos here. So let's do that. So I say y equals 77. So again, my graph is plotted and it's blue, and I know it's going to be down a little bit. So again, I can click where my graphs intersect, and I see that when y is 77, my x is approximately 3.5. So I can solve it algebraically by plugging them in, or I can solve it graphically using Desmos. Okay, so now we're looking at correlation and causation. Okay, this is that final learning target. So tell whether a correlation is likely in the situation. If so, tell whether there's a causal relationship. That causal relationship just means, did the first one cause the second one to happen? Okay, so let's look at part A, time spent exercising and the number of calories burned. These two things generally go together. That yes, I know if I spend more time exercising, then I will burn more calories. So that would be a positive correlation. And this is a causal relationship, because doing this will cause the second one to go up. Okay, so now let's look at part B, the number of banks and the population of a city. So I would imagine that yes, the number of banks would go up and the population would go up. So I would say probably a positive correlation, but these are not causal. Having a huge number of banks will not cause the population of a city to increase. So I know that that's not a causation. It's just like a random, it might just work out that way. But it probably is a positive correlation, because the larger a population, we're going to have more banks. So that happens as well. Okay, so that's just a real quick, we're just going to look at those generally. So now let's look back at our learning targets. So first we used residuals, and we really just looked at what residuals were and how we can use them to figure out if our data matches our line of best fit. The second one's a big one that we're going to be doing a lot using technology, and that's Desmos. That's going to be our biggest thing that we use. And then we looked at correlation and causation. So now that you've gone through all these, go ahead and keep working on that homework.